Okay, this is the first video for chapter 6. We're going to do the first 3 sections. So we begin with even and odd functions. So here's even. We have 2 definitions for it. One is the algebraic one, which is the f of negative x is equal to f of x. That's something you're going to want to commit to memory so that you can use it in problems. And the other definition is the geometrical one. So looking at this picture, we see that it is symmetrical about the y-axis, and that is true for every even function. We have here an example, x squared. So is x to the 4th and x to the 6th, and any simple even polynomial function. Is it true that every quadratic, for example, is an even function? No, certainly not. You can justify that either algebraically or more simply, you know that not every parabola is symmetrical over the y-axis. So they're not all even, but all the simple ones at least are. There's other functions that are going to be even. A really popular one would be the cosine graph. You know what that looks like, right? That's definitely symmetrical over the y-axis as well, and you can verify for yourself. Put in any x value that you want. Cosine of negative x is definitely the same thing as cosine of positive x. We can compare this to odd functions, which have an algebraic definition of f of negative x equals negative f of x. And geometrically, these have a rotational symmetry about the origin. So you'd have to rotate the graph around 180 degrees, and then you'd have the exact same picture. So again, y equals x, x cubed, x to the 5th, etc. Those are all odd. Sine is odd. Tangent is odd. So we should be able to check using the rules to determine whether a function is even or odd. And we're always going to do this by putting in negative x into the function and then seeing what happens as we simplify it. So here in this first one, f of negative x is 1 over negative x, but we can consider that as just being negative 1 over x, which is the same thing, therefore, as negative f of x, so this is an odd function. In our second example, we put in negative x in. We recognize that negative x to the 4th is just the same thing as x to the 4th, same idea here with the x squared. Therefore, in this case, negative x, g of negative x is equal to g of x, so it's going to be even. And in this third one, we have an example where it's neither. We get this quadratic out. It's not the same as the original, but it's also not the original with just opposite signs, so it's neither. Hey, before we move on, try to come up with a function that's defined for all values of x and is both even and odd. You might consider this algebraically or geometrically. One problem type will ask us to use the algebraic definitions to consider how we might combine functions in various ways and determine what the result will be. So in this case, we're taking the sum of 2 odd functions. We're going to show that it also happens to be odd. It would not suffice for us to just take 2 odd functions and show that their sum happens to be odd. Like, we can't just choose 2 particular ones. That might just be a coincidence for those 2. We need to show that it's true for all of them. So what we're going to do is we're going to start off by assuming that our new function h is equal to f plus g. No problem there. And we're going to say that f and g happen to be odd. Now we're going to use the definition of an odd function, which is going to require putting in negative x and then finding that our result happens to be the negative of the original. Now, so far what we've done is we're just putting in negative x for x here, which means it's going to go into both of those as well. Nothing fancy yet. Now on the right-hand side, we know both of these are odd. Therefore, we can rewrite each of them. It's negative f of x plus negative g of x. But then we can factor out that negative and make it negative f plus g. Hey, but wait a second. We know that f plus g happens to be h. Therefore, h of x is odd. And this will be true for any odd functions that we happen to choose. And you can do similar problems like this with addition, subtraction, multiplication, whatever, odds, evens, mix them up. Sometimes you'll have problems where it's like, prove that it's always this, prove that it can't be that. Lots of possibilities here. Okay, section B. Now previously, we've discussed various types of transformations of functions. Horizontal and vertical transformations, where we just slide the graph around. Horizontal and vertical stretches. Horizontal and vertical reflections. We've also seen the reciprocal of a function, which you'll recall was really just taking for any x value, we're going to change the y value to its reciprocal. This one's kind of like that. This is y equals f of x all squared. So we're taking each of the y values from the original graph and we're squaring it. And if you just keep that in your mind, then the rest of this should make sense. So we have the points with y-coordinates 0 or 1 are invariant. That's because if we square 0 or square 1, we just get the same number back again. So there's no changes happening there. It's going to touch the x-axis at its x-intercepts. It can't cut the x-axis because we can't have a negative y value come out since we're squaring the original y values. All right, so it's got to be above or on the x-axis for its entire domain. The original vertical asymptotes are going to remain vertical asymptotes. Squaring infinity, it's still basically infinity. Whenever our original y value was in between -1 and 1, when we square numbers in that range, they're going to get smaller, right? So that's going to bring the graph closer to the x-axis than it originally was. But whenever our original y value is either bigger than 1 or less than -1, then our new graph is going to be stretched further away from the x-axis. So this is kind of a weird transformation. You know, we've got, there's reflections happening because anything below the x-axis is going above. We've also got stretches and compressions happening in different places. I don't know, it's kind of neat. Let's take a look at something pretty simple looking. Let's think our way through this. So we're going to begin with the x-intercepts. They're going to stay exactly where they are. We've also got this point 4, 3. So we're gonna square 3. So that's gonna go up to 4, 9. Let's say it's right there. Now I'm going to connect these dots, but I'm gonna do it really carefully. So it's gonna look something like this. Now I am intentionally you'll notice my green graph starts off below the black graph, and then it crosses over right around here at this blue dot. And then it crosses again there. The reason I'm doing that is because let's say that had a y value of 1, so my points on my green graph need to be below the points on the black graph there. Then I continue to the left, we got to bounce up, and then to the right, we got to bounce up. If I knew for sure the original y-intercept of the black graph, then I'd be able to appropriately place a y-intercept on my green graph. It looks like the black graph is a parabola whose equation I could work out, but I'm not actually sure that it's a parabola. I'm not told that it is, so I won't assume that. Here's a professional looking version of the same thing. And you can kind of tell if you look really closely there that they do have their squared graph is underneath the original whenever it's underneath that dotted line for y equals 1. Okay, so that's squaring a function. That's kind of new to the curriculum, so there's not a ton of like past paper examples or anything out there beyond whatever we have in the textbook. But for the most part, it's not tough. It's just a new transformation to think about. And that's going to bring us to section C, which is all about the absolute value, which is what we say in the United States. Modulus seems to be more of a British English type word for the same thing from what I've gathered. So I'm sure you're aware of what this is generally. It can be thought of as the distance of a number from 0. We are going to pay really close attention to the algebraic definitions, which we've got 2 of here. The first one is that the absolute value of x can be thought of as a piecewise function. It's either x whenever x is greater than or equal to 0, or negative x when x is less than 0. It's kind of an arbitrary choice that we've decided to make here, where we say that this is greater than or equal to, and this one's just less than. I suppose mathematicians could have decided to make it greater than 0 and then less than or equal to 0, but they didn't. They decided to do it this way, so we will follow that. Second definition here, absolute value of x is equal to the square root of x squared. So we could put a negative number in here square it to get a positive, and then take the square root of it. And we see also down below how it affects a function. This is, you could imagine a linear graph here, continuing down. The absolute value of it takes the negative portion of that line and reflects it above the x-axis, makes it positive. So that's the graph of the absolute value of x, but we can also put more interesting functions in and take the absolute value of them. It's going to have the exact same effect. We could think about it using one of the algebraic definitions here. It's going to be the exact same as the original function whenever that original function had a y value greater than or equal to 0. And it'll just be the opposite of it otherwise. In other words, we're going to take any negative y values and just reflect them over the x-axis. We can also now consider, rather than taking the absolute value of f of x, we can consider f of the absolute value of x. Again, using the algebraic definitions, that is equal to f of x whenever x is greater than or equal to 0, f of negative x whenever x is less than 0. So in this case, we're going to keep any points that are on the y-axis or to the right of it, get rid of everything else, but we're going to take those values that were to the right of the y-axis and reflect them, copy them over, in fact, over onto the left-hand side. This is similar to, but it is not the same as what we did with the absolute value of f of x. So let's see here. We have a quadratic function, and we're going to graph both the absolute value of it as well as the absolute value of f of the absolute value of x. So we start here with what I think is the easier one. You could see the original parabola here. And since we're taking the absolute value of y, essentially, absolute value of f of x, that means any negative x values, y values, excuse me, are going to be reflected up. Okay, so this is what our graph is going to look like. For the second one, here's our original parabola. And then we're going to take all of these positive x values, and we copy those over here to the left of the y-axis. In my experience, this one takes a little getting used to, but you'll figure it out with a little bit of practice. Some functions combine absolute value expressions with non-absolute value expressions, and it can be difficult to figure out what these should look like without the use of technology. What we're going to do is we're going to use the algebraic definition of what absolute value is, and that'll help us work this out. So for this first one, whenever x is less than 0, we've got x, and this first x term just doesn't change because that's just x, but then it's going to be minus negative x, again, using this definition right here. Combined like terms, that's 2x. When x is greater than or equal to 0, we have x minus, and then here, the absolute value of x is just x whenever x is greater than or equal to 0. X minus x is 0. So our new function looks like this. We've got 2x, the line 2x here until we get to x equals 0. And then from there on, we have just y equals 0. We'll do the same thing for this other one. Whenever x is greater than or equal to 0, we have x times x, which is x squared. When it's less than 0, we have x times negative x squared. So we get, this is not a cubic function, although it kind of looks like it. This is part of a quadratic and then part of a different quadratic. You can essentially use this technique to graph pretty much anything. It doesn't need to be just x inside of an absolute value. That could be some other type of function, whatever kind you want. If you just use the algebraic definition of absolute value, you can get two separate functions and just graph their individual pieces. We're also responsible to be able to solve absolute value equations and inequalities. For some of these, it'll be helpful to be able to apply a few of the properties that we see before you here. Nothing too complicated there. As we're doing them, there's going to be two different ways that we can use to solve them. And sometimes one is going to be way easier than another. The two methods really are just the two algebraic definitions of what absolute value is. We're either going to kind of separate into two cases, or we're going to square both sides. So something like this, you probably learn to solve this by saying, oh, well, 2x plus 3 equals 7 or negative 7. And then you solve both of those equations, and then you get two answers. Great. And then you should always check both answers in an absolute value equation, by the way, because they might not both work out. In this case, they do. And this one here, you can actually stop right away, because you might recognize, hey, wait a second, absolute value of something can't equal a negative. Therefore, this one has no solution. Now, if you did solve this one by splitting this up into either -1 or +1, you'd get two answers, x equals 2, x equals 1. Like I said, you got to check those. If you put them in here, you would get an incorrect statement. And you get the exact same thing happening if you use the other method. So we could square both sides of this. We'll get a quadratic. You solve the quadratic, you get the exact two solutions as we get this way. You could square both sides here. You'll get the exact same two wrong solutions as you do this way. I think in both of these cases, squaring both sides was definitely more challenging, certainly more work at least, than just splitting the equation into two cases, but that's not always going to be true. These look a little bit tougher, but they're really not that bad. There's lots of ways we could proceed. Here's the first one. So we set this fraction equal to 4 or -4, and then whatever, you solve them, and you get two answers. Again, always check your work. Okay, they both work in this case. Whatever. Here, the second one. We've got an absolute value equals to an absolute value. You don't need to consider four cases in this for this type. Don't worry about the plus or minus for both of them. It ends up being the same thing. Just put plus or minus on one side, and again, you'll get two answers. And by the way, that's the same thing as what would have happened up here if, say, we multiplied both sides by the absolute value of 1 minus x from the beginning to get rid of that fraction. You would have had an absolute value on both sides, but you just keep the plus or minus on one side. Doesn't matter which. You still get the same answers. Now again, here you could square both sides if you want to, but I don't really want to. As always, we can also solve these graphically by graphing each side of the equation as a separate function and then finding the intersections. So we had an equation like this, no problem. Just take that 2x plus 3. Again, we're going to solve it twice. Once where it's set equal to 3x minus 1, and once where it's set equal to the opposite of that, -3x plus 1. We'll get two solutions. If you try to do this one using the squaring both sides method, you got to be really careful, because on the right-hand side, you don't lose that absolute value term upon the first squaring, right? Because you have 3 times the absolute value of x times minus 1 twice. So there's no absolute value of x times absolute value of x for that term to go away. So what you could do here is you could bring all of the non-absolute value terms to one side, and then you've got two options from this point. You could either square both sides again, which is going to get you this quartic on the left, which I don't really want to do, or you could separate it into two cases. So then you can solve each of those quadratics separately. You're going to get 4 answers, but you need to check all 4 of them back in the original equation, and you're going to find out that only 2 of them work. You could also have the absolute value inside of absolute value. There's no reason to panic about this. So first, we're going to get rid of the green absolute value bars. So we've still got the x minus the absolute value of 2x minus 2, and we're going to set that equal to 1. And what I'm going to do here is I'm just going to move the x to the other side of the equation to get that. And we'll deal with that in just a moment. And then we'll do the same thing over here, where we're going to set it equal to -1. And again, I'm going to move the x over to the other side. Now, each of those is going to get split. So now we're going to get rid of the inner absolute value bars, the original blue ones. So now we're going to split each of those into two separate equations to get rid of the second absolute value bars. So this one's going to go here. We take negative 2x minus 2 equals 1 minus x, but also here, in this case, I changed the sign of the left side that had the absolute value. Of course, it doesn't matter. We're going to solve both of those. Conveniently, in this case, they got to the exact same solution both times. So that's cool. And then this other one's going to get split here and here. Again, I changed the sign on the left-hand side. It doesn't matter. We get two solutions here, 3 and 1/3. This particular equation only had 3, but as you can see, since 2 of them were repeated, something like this could have had 4 solutions. Now this is not officially in the IB syllabus, but I don't know, I think it's a natural extension and something neat to look at. All right, now let's look at some inequalities. And again, we can do this two different ways. We could square both sides, or we could separate into two cases. But we're going to have to be extra careful dealing with these as opposed to equations, because, like, you know, when things are negative, that screws up inequalities and stuff. So we just need to be mindful of what we're doing. So for this first one, now they're writing it as a compound inequality. And whereas the second one, they don't. And if that's not obvious to you why, then let's consider solving it just like with equations. We could do 2x minus 1 is less than 3, so that's like the original, just without the absolute value. But then we'll also solve 2x minus 1. I'm not going to do less than negative 3. I am going to make it negative 3. But what happens with inequalities when we multiply or divide by a negative? We have to change the symbol's direction. So then when we solve these guys, we're going to get x is less than 2 from there. But here we're going to get x is greater than negative 1. And when we put those two together, we get this compound inequality. Whereas if we did the same thing on the other side, which they actually do that work here, then we get two separate answers that cannot be combined into a single inequality because we have x bigger than a larger number or less than a smaller number. You could imagine the graphs of these. We have in both cases some constant function and then some v-shaped thing. In the first case, we want the v-shaped thing to be less than the constant. So of course, that's going to happen in between the two intersection points. Whereas in the second case, we want the v to be above the function. So that's going to happen out here to the left or over there to the right. Here are some more complicated ones. Finally, the book uses the squaring method for this first one, rather than separating it into two. Okay, so we get two quadratics. We combine all the terms in one side. We're going to factor that thing, use a sign diagram, figure out where we make that inequality true. And in the second example, they're squaring both sides as well. Get rid of that denominator, multiply it over. Since it's something squared, we know it's not going to be negative, so we don't need to worry about changing the inequality. Expand, collect all the terms, factor, sign diagram. But we know in this case that x cannot be equal to negative 1. They only really make a note of it here, but that's true way back at the very beginning. We couldn't be dividing by 0. So our final answer, less than negative 1/3, or greater than 1, or equal to 1, but not equal to negative 1. I want to finish by doing one that I find kind of fun. This is the original question right here. So we have an absolute value inequality with a quadratic thrown in there. So one thing you might try is to factor out a common term of x. We have to keep it in the absolute value, though, for right now. Now, if we're going to split this up, we need to be really careful now because we have two different absolute value terms to consider. This first one, absolute value of x, we know that that's equal to x when x is greater than or equal to 0, and it's equal to negative x when x is less than 0. Okay, so far so good. This other one, however, is equal to x minus 1 when the thing inside the absolute value, the x minus 1, is greater than or equal to 0, or we could rewrite that as x greater than or equal to 1. And it's going to be equal to the negative of that, which we can say 1 minus x, when x minus 1 is less than 0, or when x is less than 1. Now, we can consider we can rewrite this entire function in between these boundary points. So we have 1 and 0, but we have to consider to the left of 0, in between 0 and 1, and then to the right of 1. So what we're going to do now is we're going to rewrite the function, but we're going to consider three different regions, three different domains. One when we are less than 0, one when we are in between 0 and 1, and one where we're greater than 1. So in the first case, when x is less than 0, the absolute value of x is going to be negative x, but the absolute value of x minus 1 is going to be 1 minus x. So that gives us a quadratic, which we can factor, and we get these solution regions out. However, because we originally assumed that x was less than 0, we need to eliminate the possibility that x could be greater than 2, because that contradicts the assumption for this entire portion of our work. In the second region, if we're greater than 0, means the absolute value of x is going to be x, but we're still less than 1, so absolute value of x minus 1 is still going to be 1 minus x. Put that in, that gives us another quadratic, which ends up having no solution. So we can ignore this entire piece. That gave us nothing. And then in the third section, when it's bigger than 1, the absolute value of x is still bigger than 0, so that's going to be x. And then the absolute value of x minus 1 is now x minus 1. That gives a quadratic. Oh, it's the exact same quadratic as we had before. So obviously it's going to have the exact same solutions. In this case, we have to ignore that portion because we assumed that x was greater than or equal to 1. So our overall solution in this case ends up being x is less than negative 1 or x is greater than 2. It was a coincidence in this case that we ended up getting the exact same quadratic in both sections. So it's very possible, given another question, like maybe that would have been a different number than what we had over there. So it is crucial that we check both of them. We can't just assume, oh, I'll just take both answers from one of the sections. Like, no, you can only take solutions that actually match your assumptions. This is just a coincidence that they matched up. Now, we could have also done that one by squaring both sides. And then rather than expand this to get some ugly looking quartic function that we don't know what to do with, just recognize that this is a difference of two squares, which means that we can rewrite it as x squared minus x plus 2 and x squared minus x minus 2. And these are the exact same two quadratics that we just saw on the previous screen. So we already know that this quadratic will really contribute nothing because that quadratic is positive definite. For any x value, this entire term is positive. So we really don't even need to worry about it. We just consider the sign diagram for this one, which we already worked out on the previous page. In my experience from the previous curriculum, I would say that the function transformation section of this video is, well, it's the easier part in my opinion, but I also think it's the part that was more important from the perspective of what shows up on IB exams. There are plenty of questions involving that. You certainly need to know about even and odd functions. That's going to be very important throughout the course. And I think given that the square of a function is a brand new topic that they've decided to include in the syllabus now, I would definitely know that. Solving absolute value equations and inequalities, it's always been on the syllabus, but it's not something that was ever really a major focus. So in my opinion, that's actually one of the harder parts of this section because you have to really be very careful about applying the rules correctly, but I think it's less crucial for us to know. Maybe I'm wrong. I don't know. Hopefully not.